Okay, so last time we were together, we started talking about the BFFs, and we got the first 3 of them done. Okay. At this point, you should have all of the 1-1 homework done. You should have the 1-2 homework done. That was the video lesson. And you should be working on the 1-3 homework. We do split this chapter into 2. So we'll be having a test over 1-1 to 1-4, which isn't going to be that far away because we're not halfway, but we're a little bit into 1-3, and all we have left is 1-4, and then we're done with that chunk. So don't let yourself fall behind. You need to be working on these problems. Tomorrow, we will have a little quiz-a-coo over some of the 1-1 didn't really have any big concepts in it, but 1-2 had a ton. Things like domain and range and asymptotes and all that stuff. So tomorrow we'll be having a quiz over that. I want to get through a couple more BFFs, and then we'll look at some practice work here for that quiz. All right, but first we got to get through a couple more BFFs. So let's get your sheet out. And let's look at number 4. Well, they're not numbered, but you know, the 4th one. This one is called the reciprocal function. And its picture you've seen before. I didn't know it was a reciprocal function. Has an asymptote at x equals 0 and an asymptote at y equals 0, and looks like this. That is a picture of y equals 1 over x, the reciprocal function. Some people refer to this as the rational function because it's a fraction. And fractions are rational numbers. Now, let's talk about these asymptotes for a minute. This asymptote is here because x cannot be 0, right? And in the 1-2 lesson that you were supposed to watch on the video, it tells you that vertical asymptotes happen when the denominator is 0. So you can't have a 0 down there. Now, this asymptote happens. Can anybody tell me about the horizontal asymptote? Anybody that watched the video? Well, then just think about, watch the video so you know. But think about this for a second. As you let x get bigger and bigger and bigger, what happens to this fraction? It gets smaller and smaller and smaller. Now, will this fraction ever equal 0? You'll have 1 over a million, and 1 over a zillion, and 1 over 83 million trillion zillion, right? But it's never going to quite get to 0, but it's going to get closer and closer to 0. That's why you have that horizontal asymptote right there. So, we talk about the questions then. What's the domain? What's the domain of this? Everything except 0. X cannot be 0. So when we write that down, we can either write x can't be 0. That's absolutely fine with me. If you want to look like a mathematician, you'll say everything from negative infinity to 0, or from 0 to infinity. What's your range?
Pretty much the same thing.
Exactly the same thing, only it's y can't be 0. Because this arrow goes down forever, this arrow goes up forever. Remember, range is y. Range is y. I'm looking up and down. The only thing I don't do is cross at 0, right? So I've got everything above 0 and everything below 0, but not 0. Is this thing continuous? No, you cannot draw it without lifting your pencil. Right? Where is the discontinuity? Where is the break? The break is at 0. So this is discontinuous at x equals 0. That's where the curve is broken. Is it increasing or decreasing? Now, kids, remember, when I answer this question, I trace my picture left to right, right? So left to right, which way is my pencil going? Down. So it is decreasing, right? Left to right, which way is my pencil going? Down. This is a decreasing function. This is a decreasing function on its entire domain. It's decreasing on its entire domain.
You always go left to right when doing
Always left to right. Just like you read.
Okay, this might be a dumb question, but even though it's decreasing at the top, it's going like bigger in x's.
When we talk about increasing and decreasing, we're talking about going up and down. X is sideways. Now symmetry. Now remember, we're talking about the symmetry with the x-axis, y-axis, origin, and identity line. Okay? Those are the symmetries we're talking about. There can be other symmetries, but these are the 4 we're focused on. So, if I were to fold my paper on the y-axis, do I get a mirror image? No. If I fold my paper on the x-axis, do I get a mirror image? No. If I flip it across the origin, do I get a mirror image? Yes. So this has symmetry about the origin, which, oh, by the way, means it is odd. So this is an example of an odd function. Does it have symmetry about the identity line? This is the identity line right here. If I folded my paper on the identity line, would the curve double back on itself? Yes. So this one has 2 symmetries. It's symmetric about the origin, and it's symmetric to the identity. Is it bounded? Does it have a ceiling and a floor? No. Now, if you looked at only one piece of it, then this piece would be bounded above, and this piece would be bounded below. But we're not looking at pieces, we're looking at the entire curve. It is not bounded. It goes up forever and ever and down forever and ever. Does it have any hills and valleys? Remember, local extrema are mins and maxes. Are there any mins or maxes in that picture? None. We already did the horizontal asymptote and the vertical asymptote, so now we're going to do the end behavior. Now remember, the end behavior is the limit of the function as x approaches infinity, and the limit of the function as x approaches negative infinity. Okay, so as x approaches infinity, Taylor, now I'm looking at x. What's happening to the y values as x approaches infinity? As I head off the page this way, what's happening to my y values? They're getting closer to 0. So your end behavior, you're approaching 0. Now, what happens when I head off the page this way? They're also approaching 0, right? Now, we got to make a distinction though, because this approaching 0, see how the curve is coming down, 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 getting closer to the asymptote. This one is going up, 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 getting closer to the asymptote, right? To make the distinction between approaching from the top and approaching from the bottom, we put a little plus sign if we're approaching from the top, and a little minus sign if we're approaching from the bottom. That tells our reader, whoever's looking at our information, that they're both ends are going to 0, but one's coming from the top side and one's coming from the bottom. All right? If you had a picture that looked like this, which is possible, then this one would be 0 from the top, and this one would also be 0 from the top. All right, now we've got our square root function. Which looks like this. Now, that shouldn't be totally confusing for you. We all know what x squared looks like, right? What does x squared look like? Oh my, we should know this. It's one of our
Parabola.
It's a parabola opening up like this, right? From last year, do you remember what happens if it's y squared and not x squared? It opens sideways. Now, this is not one of our BFFs. Why is that not one of our BFFs? BFF, basic family of function.
It's not a function.
That's not a function. So if I want to have that idea, but I want it to be a function, I have to take off a piece of it, right? Would you agree with that?
Sure.
So basically what I'm doing is square rooting both sides so that I have y equals the square root of x, and that gives me my square root function. Okay, so what do I want to know about it? What's its domain? Be careful now. What's its domain? And everything bigger than or equal to 0, right? So that would be 0 to infinity for my domain. And again, if you look at the problem, that makes perfectly good sense. What happens if you put a negative number in here? You get eyes. Not good in BFF land. We want to keep it real, right? Keep it real. All right. What's my range? Same thing. We're starting at 0 and going up. So that is my domain and my range. Is this a continuous function? Can I draw it without lifting my pencil? Yes. No asymptotes, no breaks, no weird stuff going on. Increasing or decreasing? Increasing on its entire domain. It's always going up, 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 up. Does it have any symmetry?
No.
Any of these four? No. No symmetry. You can flip it around and do stuff to it, but it won't double back on itself. Is it bounded?
No.
Actually, it is. Remember what, now it's not bounded, but it's bounded below, right? Remember, bounded, when we talk about bounds, we're talking about ceilings and floors. This does not have a ceiling. That keeps going, I didn't draw it very well, but it keeps going up, 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 up. Doesn't it have a floor? So we say it's bounded below at y equals 0. That's the floor. Right there's the floor. Does it have any maxes or mins? Any high points or low points? No. Well, you gotta be careful. A relative minimum is the bottom of a valley. So no. Does it have an absolute minimum point? Yes, it does. This is its absolute minimum point. But that is not really considered, this is kind of picky stuff, so I'm not going to be too hung up about it. When we talk about maximums and minimums, we're generally talking about curves that look like this, you know, this kind of thing. And this would be a maximum and this would be a minimum. I will agree with you that if we are talking about an absolute minimum point, you could call that the absolute minimum. That is the lowest point on the curve. No asymptotes and behavior. This one does not even have end behavior to negative infinity. It only has one end to it. So what is the limit of this function as x gets bigger and bigger and bigger? What happens to the function? It goes up, 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 so it's positive infinity. All right, then we've got our exponential function. Is this period regular length? I want to stop in time to do a little review. Okay, the exponential function is y equals e to the x. Now, e, you've seen before. When you did natural logarithms last year, ln's, e is what's known as Euler's constant. Euler, not Euler, Euler's constant. That's why it's E. And it is approximately, anybody know what it is approximately? It's like pi. It goes on forever and ever and ever. Do you know what it is decimally? 2.718. The characteristics of the exponential function, though, are not dependent on E. This could be 2 to the x, 3 to the x, 8 to the x, any number. It just happens fundamentally, we say e to the x. Now, this point is the point they'll all have in common. If you put a 0 in for x, you're going to have e to the 0th, which is what? 1. If this were 2 to the x, and you put a 0 in for x, what's 2 to the 0th? 1. So the base, irregardless of the base, the point that you'll always plot is 0, 1 on the parent graph, on what's called the parent graph. You'll always graph the point 0, 1. And then this is what your exponential looks like. All right, so going through this stuff, what's the domain? That's x. What can x be?
Anything.
No, x can be everything. There is no number x can't be. Your domain is everything. So you can either say that or you can use the symbol for real numbers. The domain is all real numbers. X can be absolutely anything you want it to be. Not range, though. What about the range? The range is 0 to infinity, and unlike this one, where 0 was included, it's not included here because actually this is an asymptote. You have a horizontal asymptote at y equals 0. You have no vertical asymptote in this picture, but you do have a horizontal asymptote at y equals 0. And here's why, gang. If you raise 2 to a power, will you ever get a negative number? No. You can raise 2 to a negative power, but that just makes a fraction. It doesn't make a negative number. You can't raise a positive to a power and get anything other than a positive. So the whole graph is up here. Okay, continuity. Is that continuous? Yes. Increasing or decreasing? The whole thing's increasing. Does it have any symmetry? Any of our special symmetries? No, none. Is it bounded? It's bounded below at y equals 0, but not bounded above. So it's just bounded below at y equals 0. No hills and valleys. We got a horizontal asymptote already on there. No vertical asymptotes. And behavior. That's the limit as x approaches infinity. And the limit as x approaches negative infinity of our function. All right. So here we go. What happens as we approach as x approaches infinity? As you go off the page on the right side, what happens to your curve? It goes up, 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 positive infinity. Now what happens to the picture as you go off the page this way? What's the curve doing?
closer to 0.
Getting closer to 0, and we just talked about we want to be even more specific than that. We're getting closer to 0 on the top. So that's going to be a plus on the top. Now this is a perfect one. I'm gonna stop here for a minute because I want to do some review. But this is a perfect one to make sure you understand the translation or the transformations that we talked about the other day. So let's suppose I want you to consider this problem, and I want you to consider this problem. Now they are very different problems.
Oh, I think I
They both have the same parent graph. They both have the same shape. But this +2 impacts the picture differently than this +2 does. Okay? Oh, you're graphing this? Is that what
Yeah.
Okay. Now let's try it without our calculator. All right, so this is the shape that I'm starting with, and this is the point 0, and this is the shape that I'm starting with. That's what my exponential looks like. What does a +2 tacked on the end of the function, what does that do, Patty?
That increases the y-intercept, so you move up 2.
It takes the whole picture and lifts it up 2.
Move it up 2.
So instead of being at 0, 1, it's now going to be at 0, 3.
But the shape remains more or less the same.
And instead of the asymptote being at y = 0, everything got shifted up. So now my asymptote is at y = 2. And like Patty said, I have exactly the same picture. It's just picked up 2 units. So if you had this one, remember what that looks like. That looks like that. So this would take that picture, and instead of starting at the origin, it would start up here at 0, 2. You gotta have the shapes memorized, people. Okay, so start memorizing them. We're only halfway through them. Now, what happens when we hook that 2 directly to the x? See, it's in a different position. It is grouped with the x. What happens to the picture then? It moves sideways. And like always, it's the opposite of what you think. So x + 2 is actually going to take this, you know, our basic picture, and it's going to move it 2 units to the left. So it's just going to shift over here, and you look like that. Oops, I don't know why I dashed that. That one's a little harder because we don't really label points on that. One's a little harder, but it shifts 2 units to the left. So if we had this one, notice how the 2 is grouped with the x. So that's going to be a shift 2 units to the left. So instead of starting here and going like that, it's going to start over here and go like that. Is that right? Okay. All right, let's get out our packet from this chapter. And turn to, oh wait, we're not ready for that one yet. Well, all right, turn to, I think it's the 3rd page. It says Precal A period 5 quiz 1-2 to 1-3.
Yeah.
There are a couple of these we're not ready for yet, and there's one new piece. Well, it's not new, it's in the video, but we haven't done it together. So let's look at this. this will be some learning going on. So we're on, I think it's the 3rd page of the pack. Well, I don't know, maybe it's on the 2nd page. I stapled my assignments to the top. It says Precal A period 5 quiz. It's got these 4 little pictures down here. Some of which we haven't studied yet, so. All right, so the first question though, this is great, this is a great problem, if I do say so myself. All right, so somebody said, you look at it, and if you have blood flowing through your veins, you simply cannot not want to factor it. I mean, that's just what that's just what you do. So you look at it and you take out a 2. The bottom is the difference of squares. The top still factors some more. And then I notice something that doesn't happen all the time, but sometimes after you get everything all cleaned up here, factored, what do you notice? You can cancel.
Yeah.
So what we are essentially going to graph is this. Now, you are not being asked at this point. We will soon be graphing, actually physically, literally graphing this. All you're asked for right now are the asymptotes and the holes. Now, who watched the video and remember where holes come from?
It's what you cancel.
It's what you cancel out. There are 2 ways, actually there's more than that, but right now there are 2 basic ways that you can be discontinuous. What does discontinuity mean? I removed my pencil. So it's a break in the curve. There's 2 ways right now that we can have broken curve. One is literally a vertical asymptote. That splits your picture. So we're going to have a vertical asymptote at -3. Okay? Your vertical asymptote's at -3. Why? Because that makes the denominator 0. And you can't have a 0 in the denominator. Ever. Math sure says so. Now, in the original problem, not only could x not be -3, but x also couldn't be +3 in the original problem, right? Could I put 3 in my new problem? All right, let's do that. What happens when I put 3 in my new problem? I get 8/6, which is 4/3. That means in my picture, at the point 3, 4/3, there is a hole or a skipped point. Not a massive break. I mean, this is like an earthquake crevice here. I mean, this splits it. This is just a little open point. So when I graph it, which we're not doing, it's going to skip right through there. It's just going to skip that point. So how did I know to put a vertical asymptote at -3? Because I can't get rid of that, right? X simply can't be -3. X can be 3 in this problem, but it can't be 3 in the original, so it gets plotted as a hole, an open dot. The only way then that you can get holes is if what happens in your problem? You cancel. Many problems will not have holes. The only way you can have one is if you can cancel out. And whatever x value you canceled out, you plug it into your new problem to get the y value, and that's where your hole is. If you had a problem like this, kids, there will be no hole. Do you understand that? There will be a vertical asymptote. Where will it be? At 2, x equals 2. But there's no hole. All right. Horizontal asymptote. Oh, there's a horizontal asymptote, all right. Where is it?
Sorry, I don't understand. You said that there's no hole, but can you kind of explain it?
The only way I can have a hole is if I can cancel.
Okay.
If I can't cancel, I'm not going to have a hole. Where's my horizontal asymptote?
2.
At 2. Who said that? All right, Caitlin, how did you know that? Oh, let me guess. Did you watch the video? Oh, yes! And it's all explained there. Go ahead, tell us.
So it's y equals, so you look at the x's, it's 2 over 1.
It's 2 over 1. It's 2 over 1. If you think about letting x get huge, like trillions, you've got 2 trillion squared over 1 trillion squared. Now, I know you got some other stuff, but if you're talking about a trillion squared, none of this matters. So you've got 2x squared over x squared. Your horizontal asymptote is at y equals 2. Where would the horizontal asymptote of this problem be? Y equals 1. Remember, your horizontal asymptotes are y equals equations, and your vertical asymptotes are x equals equations. If you start getting that confused, whatever axis it crosses is what letter it is. So when you draw a vertical line, it crosses the x-axis, so it's x equals -3. Y equals 2, because it crosses the y-axis at 2. All right. Let's try one more. Like that. Are we out of time? Almost. All right, here we go. So let's factor real quick. Everybody good with that? Remember, you don't have to graph it. All you have to do is tell me where the asymptotes and holes are. Is this problem going to have any holes?
Yes.
Yes, it is. And the hole is going to happen at 4, where x is 4. My new problem is just x plus 4 over x minus 1. How do I get the y coordinate? Remember, the hole is a point. How am I going to get the y coordinate? I just plug in 4, so I get 8/3. So my hole will be at 4, 8/3. Now, is there still a vertical asymptote?
Yes.
Yes, and the vertical asymptote is at x equals 1. Because if you put 1 in, you're going to get 0 in the denominator. And where's your horizontal asymptote?
Also at 1.
At y equals 1. Okay?
When you look for the horizontal asymptote, do you look at the original or the final?
For the horizontal asymptote, it doesn't make any difference at
Okay.
all. Now, anything associated with y, which would be the horizontal asymptote and the y-intercept, you can look at the original. Everything associated with x has to be looked at over here. So I just suggest to the kids, just look at this one all the time, but it would be okay on that one. Okay, so tomorrow, oh, is it only 8:30?
Yeah.
Oh, we got 5 more minutes. Yay, okay, all right. So what else are we going to have on the quiz tomorrow? On the quiz tomorrow, I feel completely justified in asking a question like this. Is the cubing function, or the cubic function, you could use either word, cubing or cubic function, even? And why or why not? This is a guess question, yes or no. You need to explain it to me. All right, now, this is a massive question. It looks simple, but it's massive. First of all, you have to know what the cubic function looks like, right? So that's one of our ones that we've talked about. I'm not going to ask you about the ones we haven't talked about. So there's 6 that we've talked about. So this is one of them. The cubing function looks like this. All right? Then you have to know, what's it mean to be even? Even means you have symmetry about the y-axis. So if I fold my paper on the y-axis, does this double back on itself? No. So the answer is no. Why not? There is no symmetry about the y-axis. Okay? So another question might be, is the exponential function continuous? Why or why not? Okay, so first thing you got to know is, what does the exponential look like? It's one we just talked about today. Looks like this. So, is it continuous? Yes, it is. And why? I don't have to pick up my pencil when I draw it. Now, in calculus class, your professor's probably not going to love that definition, but that's how we're thinking of it. Okay?
What would be the right answer with that?
Honey, you don't want to know the definition of continuity. It's in 3 parts, and it's wild and wacky. Yeah, just, it's continuous. It has to do with limits, and we haven't even talked about those very much yet, so. Yeah, so that is continuous. All right, and one more potential question. Sketch. Now, this will be no calculator. Freehand sketch. Nothing perfect, like I've been doing here. This kind of thing. Sketch. All right, now, first of all, you got to know what shape that is. That's the quadratic or the squaring function. We know what shape that is, right? Now notice that 3 is not grouped with the x. That would be something different. That 3 is just kind of stuck on the end of the parent function. What does that 3 do then? So the function lowers it 3. So you would somehow indicate that this is the point 0, -3, and that's all you have to do. All right? So, just so you know, I'm envisioning a quiz tomorrow that would have one problem on it where you have to do holes, vertical asymptotes, and horizontal asymptotes, and then maybe 3 or 4 questions like these about the 6 BFFs that we have already talked about. Got it? Okay. No. This will be all no calculator. One page. One page. Okay, everybody ready? Got it? And don't forget, put in your planner, we need mathlete. Did you sell your wrap?